Hello, everybody, and welcome to Data Talks. Today, again, we've got on our guest, Seth, who's going to be explaining more about GANs. If you've not seen the first Data Talks, I definitely recommend you see it. It's going to be up in this link above, so if you click on that link, you'll go ahead and you'll check that out. If you're new to this and you just don't want to watch the previous video, I'm Nate. I'm a data scientist. I teach data science in the city. Seth, do you want to go ahead and introduce yourself?
Yeah, I'm a data scientist as well. I've taught data science both in Chicago, and now I work for this company that goes around to different companies and teaches their employees all the different parts of data science. So I'm personally really passionate about deep learning, and so I love explaining the concept behind it, and so that's the motivation for doing this GANs thing.
Cool. I think we're all excited.
All right. Cool. So I want to cover one quick thing.
Mm-hmm.
We'll put the link above to this. Last time we were doing this before I gave a talk at ODSC on GANs.
Mm-hmm.
Since giving that talk, I had some examples of GANs in PITorch. Now, last time we went through an example in TensorFlow.
Yes.
TensorFlow is awesome, super detailed. PITorch is sort of the new cool framework, and we could probably devote a whole nother podcast to just talking about PITorch versus TensorFlow. But the short version is you can check out code that might be easier to follow than what we showed last time. It codes up a GAN. Just want to make that point.
Awesome. We'll include it in the link in the description.
Sweet. All right. So we talked about the basics of what GANs are, like step by step, how they work, and what's going on last time. So let's talk about some of the most famous architectures. So the first one that was a big step forward from the original version of GANs, which didn't actually use convolutions. Even though they were generating images, they just used good old-fashioned, fully connected layers, and those were actually able to generate images. But a huge step forward was making deep convolutional architectures work with GANs.
Okay.
And this is and the big result was published in January of 2016 in sort of the famous paper known as the DCGain paper, or Deep Convolutional Generative Adversarial Networks. And
Do you have any? So I don't want to go into convolutional neural networks here. But do you have any good resources that you liked learning convolutional neural networks from, so other people can learn about them if they've heard of what a convolution is?
Yeah. I think a great place to start is the TensorFlow or PITorch documentation, walking through those tutorials. If you're interested in convolution specifically, the Theano documentation of all places actually has a great breakdown of convolutions. And I have a little GIF here from that documentation that explains what's going on and even shows you sort of, and I'll get to this later on. But for convolutions in particular, they can be very tricky. And the Theano documentation has a really good breakdown of what's going on in convolutions.
Awesome.
Interestingly. Yeah. So this paper sort of really pushed GANs forward. And there were a couple of things that made it work. The first was this deep convolutional and deconvolutional architecture, which we won't go into in detail. But the other one was batch normalization, which had been invented the prior year in 2015. And this paper was its first application to GANs. So we'll talk about what that is in a second. And first, a crazy fact that I'm sure makes me feel very depressed. Nate, I'm sure it makes you feel very depressed. Alec Radford, the lead author of the DCGain paper, was still in college when it was published.
This is as an undergrad?
He was as an undergrad at the Olin Engineering College, which is in the Boston area, I believe, right? Yeah. He was still an undergrad there. Crazy. And one of the other authors was Sumit Chintala, who is now the lead author of PITorch.
Right. No, that's right.
Yeah. So just some DCGain results. When I presented this at ODSC, I sort of gave the audience this question of which of these 5 bedrooms do you think are real? Here's a photo of a bedroom, 64 by 64 pixels, color image. Here.
I feel like this is going to be a trick question, Seth.
Well, Daniel, it turns out everybody in the audience also realized it was a trick question. They were all like, they're all fake.
And then is it a double trick? Are they all real?
And they're all real.
Okay. Which one is it?
And they're actually all photos of bedrooms I've been. No,
Oh my!
just
Wow.
my friends' bedrooms. Actually, no, they're all fake. They were all generated by a deep convolutional GAN.
Yeah. Yeah.
So some really cool visual results from this paper. One goal, so deep learning sort of has two really big high-level goals. One is sort of prediction.
Mm-hmm.
So taking an image and predicting what's in it, or predicting where the bounding boxes are that say where objects are in images, for example. But another is just a little more general, which is just representation learning.
Mm-hmm.
So it's just, there's a notion of a bedroom out there. We have some notion of what it should be. It should like have a bed. It should have maybe some windows. It should have a lamp beside the bed. It should have a dresser and so on. And the question, one thing deep learning attempts to do is create a mathematical representation of that. And what that means is like a vector that represents what a bedroom is, or represents or at least a neural network structure that can take a vector and transform it into some kind of bedroom. And one goal of DCGain and embedding. Ooh, there you go. Bedroom to, an embedding. Oh my. Oh my. I need to stand up. I need to take a break.
No, don't.
All right. Okay. Bed to vec, you know?
Yeah, bed to vec.
Bed to vec. Right. Bed to vec. All right.
Sorry.
One extremely cool, I think this is actually a very mind-blowing result from this paper, was that they were able to show that the GAN hadn't just sort of learned how to generate this bedroom and this bedroom and this bedroom. It had learned a whole space of bedrooms. Now, how did they show that? Remember how GANs work. You start by taking a 100-dimensional vector, randomly generated, and you feed it through a neural network architecture, deconvolutional structure, and you end up with an image. So in theory, if we have vector 1 and vector 2, and both of those images generate bedrooms, if we take any vector in between those two images and feed that vector through this neural network architecture, each one of those should also generate a bedroom. So, and just like for the audience, it would be, you wouldn't have a very good GAN if the following happened. If this vector generated a bedroom and this vector generated a bedroom, but everything in between was just like random weird noise and didn't look like a bedroom at all.
Yeah.
That would be a sign that you were more just memorizing the training data and not actually learning a notion of what a bedroom was.
Yeah. Yeah.
So this paper showed that this architecture did in fact learn what a bedroom was. So let's have a look at this. Here's one bedroom generated by one 100-dimensional vector. All the way over here is another bedroom generated by another 100-dimensional vector. And if you look in between, this is the linear interpolation between those two vectors and all of the bedrooms that it generated. The crazy thing is, even though, check out, this one doesn't really have a window in it, and this one has a huge window.
Yeah, that's right.
Let's now look, every one in between kind of looks like a bedroom. Yep. This looks like a bedroom. This looks like a bedroom. Here you kind of have the emergence of a small window. This looks like a bedroom. So does this, so does this, so does this. It's pretty amazing.
Yeah.
Yeah. So it's sort of learned what the space of bedrooms is.
The definitely the deep learning book goes into representational learning quite a lot. I think Goodfellow's a really big fan of it. So if you're interested in that, definitely check that out, and it will be in the description below.
Yeah. Cool. So another thing is, and this is less pertaining to GANs, but it's also it's very interesting. So the discriminator is another part of it. So these are generated by the generator up here. The discriminator is also is trying to distinguish whether an image is of a bedroom or not. So this also sort of supports the idea that this has learned important and reasonable visual characteristics of what a bedroom should be. These filters are the filters that the network has learned to detect whether an image is of a real bedroom or is a fake image.
These
So,
are the first level filters applied to random images?
I was just thinking that. So these are the last layer.
Oh, the last layer. Oh, I see.
So,
Sorry.
yeah, no. So they would be, I guess, with convolutional neural networks, the visual field of the last layer gets like bigger and bigger. So
Mm-hmm.
I imagine that's why these are like high resolution kind of images.
Yeah.
Uh,
Yep.
so, but it's interesting to look like if it sees this kind of pattern, it knows that, oh yeah, it's probably a bedroom. If it sees this kind of pattern, it knows it's probably a bedroom or probably not a bedroom.
Mm.
Same with, you can see all these bedding type patterns, etc. Yeah, I know it sounds like embedding, right?
Yeah, I know. It's sorry.
Don't laugh, Nathaniel.
No, it definitely looks that way.
Yeah. So that's also interesting.
Okay.
Finally, they applied the same architecture to faces, and they got this famous result, which has since been improved a lot. These examples now look kind of creepy since these are from 2015.
Very much so.
But it's just shows that GANs are able to do representation learning as opposed to just generating images that kind of look like a thing.
Mm-hmm.
So, for example, if they take a vector that generated an image of a smiling woman, take a vector that generated an image of a neutral woman, subtract that off, add the vector of an image that generated a neutral man, that generates images that look like smiling man.
Mm-hmm.
So it has learned all these concepts and represented them in a lower dimensional space.
Yeah, pretty cool. This is pretty similar to like the word embeddings that were done by Milikov back in the day.
Exactly. That's exactly right. This is the visual analog to
basically.
France minus Paris plus Rome equals Italy. That kind of stuff.
Yeah.
All right. So one thing that made this work, the reason they were able to get such great results as opposed to Goodfellow's original GAN, was that they used this deep convolutional architecture.
Mm-hmm.
And their architectures become sort of famous. The number of filters they use, the number of hyperparameters they use have been repeated and sort of like used as inspiration for many other architectures. So I have like a diagram of the architecture here, and code this architecture up in PITorch. What?
Then torch.
Yeah.
Yeah.
So here you go. There's the DCGain architecture. There's the discriminator. There's the generator. Yeah, we can go through the code. This is all in the notebook that we'll put.
Yeah, please.
So, no need to go into that.
Yeah, I do find it funny. I've literally for the past week been watching PITorch tutorials and sort of been playing around with it.
Yeah, it's great, right?
It truly is. And this is coming from someone who's used Keras and TensorFlow for like 2.5 years or something like that. Yeah, it's somewhat sad though.
Yeah, well, I don't know if we want to get into this here, but I was just talking to someone a couple days ago about how TensorFlow is really good if you want to go to production, because you have just a static graph and that's easy to put into production. PITorch, they're working on that and they'll get there, but it's not there yet necessarily. Is that your understanding?
I think that's true.
Yeah.
It's one of those things though, as sort of a data scientist, you spend most of your time working with non-production code.
Yes.
So
but maybe that's not the way data scientists should work. Maybe they should think more about how is this going to go into production if they're working for a company.
It's true. It is true. Instead of just handing it off to the software engineers.
Yeah, exactly.
Job well done.
Right. No. That being said, for those of you listening, if you're doing side projects or if you're doing research type things, PITorch is a great way to go.
Very much.
PITorch has really caught on in the research community because researchers don't need to put it into production a lot of the time. They just produce a result. And there you go.
Okay, we're going to convolutions.
Yeah. I'll just briefly cover convolutions. So like, what's going on with convolutions? Like, this confused me a ton when I was first learning about this stuff. So like so for example, this is the famous AlexNet architecture, the first big convolutional architecture. So like, what's going on when you start with a 224 by 224 by 3 image, and you do some convolution thing, and then you end up with a 96 by 55 by 55, like, and the convolution size is 11. Like, what's going on there? So I actually have done sort of coded up convolutional neural networks from scratch. So we don't need to go into that now, but maybe we'll post a link to that. But at a higher level than that, convolutions are the following operation. So if the blue is our original image, and the gray is our convolutional filter, and the green is the output image, what's happening is this convolutional filter is being slid over our original image, and at each one of these points, the dot product of the filter and the pixels from our original image are being taken and put into the output image. And if you read, maybe we'll put some links about like classical computer vision techniques. People can design these 3x3 filters that can do things like detect vertical edges or detect horizontal edges. And what a cool thing is, it turns out that if you just give a bunch of these filters to a convolutional neural network with the right hyperparameters and so on, it can actually learn to look for things like horizontal edges or vertical edges.
And the original VGG paper, has their their first and second and third filters, and even in the first level filters, it's basically just looks for edges, different colors.
Yeah, I didn't know that. That's cool.
Yeah. So Jeremy Howard does a great version of this. He does convolutions in Excel. Which is really fun. You should check that out.
You all should check that out. I've seen that. It does a great job of breaking down a lot of these concepts. All right. So I think one thing that's interesting is AlexNet. Yeah, go ahead, Nate.
No, nothing.
Yeah. Like in the AlexNet architecture, you have these 11 by 11 filters. Now, what does that mean? Well, there's 3 channels in the original image. There's red, green, and blue. And so what actually happens, and I just didn't really learn this until I really went deep and got into what was going on in the code, is there's an 11 by 11 filter slid over the green channel of the image. There's another 11 by 11 filter slid over the blue channel of the image. And there's another one slid over the red channel. And then those 3 are combined to create whatever the sort of outputs are in the next layer.
Right. It's like an 11 by 11 by 3 matrix.
Yes, exactly. So a cool thing is you can't always do this with filters, but when your starting image is 3 channels, red, green, and blue, and your filters are 11 by 11, you can combine those 3 11 by 11 things together into one sort of color image that just has a red, green, and blue component. And you may have seen this visualization before. But that is exactly what these are. I think maybe a lot of people have seen this visualization, but understand it in terms of that 11 by 11. If you look at these are actually 11 by 11 images. There's 1, 2, 3, 4, 5. There are 11 pixels by 11 pixels in every one of these 96 images. So again, what these are the components of an image that the convolutional neural network learned were important to classify what was in the image, in this case, to classify which of all the 1,000 ImageNet classes it was. And what these really are is these are the red, green, and blue components of the filters that it learned all smashed together to make one color image. So that's what these were the 96 filters that the first layer learned. Yeah. So hopefully that gives you a little better idea of intuition of what's going on with convolutions.
Okay, cool.
Right. So that's sort of like the first thing that the first innovation was the whole deep convolutional architecture.
Okay.
This is a big typo. This should say batch normalization. The second trick was batch normalization.
Yes.
Yeah. All right.
The comments now make sense.
Right, exactly. Okay, what is batch normalization? It's like an incredibly simple and elegant trick. It's really unbelievably simple. So it was introduced by 2 researchers from Google in March of 2015, about 9 months before the DCGain paper came out. And what is it? So for a normal neural network, we have our input layer, hidden layer, etc., and then eventually our output. Now, we know that usually these weights, the things connecting each layer, are randomly initialized.
Mm-hmm.
And we know that to help those weights learn the right relationship between our features and what should be in the hidden layers and ultimately what should be in the output, it helps to scale our input.
Mm-hmm.
Like if one feature is on a scale from 0 to 1,000 and another feature is on a scale from 0 to 1, then what's going to happen is these weights are first just going to have to learn that, whoa, these weights are going to have to be 1,000 times smaller than the weights for the feature from 0 to 1, just because they are. So like that's just going to confuse our network. It could get around that problem, but it would just take more time to train, yada, yada, yada.
Sure, yeah.
So what these researchers from Google just said is like, well, that same argument applies further down in the network.
Mm-hmm.
If we cover up these first two layers and just look at hidden layer 3, well, we kind of want all of these to be on the same scale.
Mm-hmm.
And so maybe each time we feed things into a layer, we should normalize them and we should put them on the same scale. And that's what batch norm does. And intuitively, it works for the same reason that normalizing data before feeding it into a neural network works.
Mm-hmm. Mm-hmm.
You're not changing that. You're not like making this feature all of a sudden larger than this feature where it was smaller before. You're just kind of making the scale more reasonable.
Yeah, that's true. Yeah.
So how it's actually done. So you might say, wait a minute. Like, let's say right here, it looks like I have 9 features. How do I like normalize these features? What does that actually mean?
Mm-hmm.
Like I said, we don't want to really if this feature is just higher than this feature, we don't really want to change that. But keep in mind what's actually going on in neural networks is we're feeding images through a batch at a time.
Mm-hmm.
So for each one of these 9 features, we're getting like 64 different values if we have a batch size of 64.
Mm-hmm.
For this one, we have a batch size, we're getting 64 different values and so on. And so what we want to do is we want to normalize, we want to take these 64 values here and subtract the mean, divide by the standard deviation to get it on a scale of, to get this feature normally distributed. And do the same thing for this feature, the same thing for this feature, and so on.
Mm-hmm. Mm-hmm.
And that's batch normalization.
Yep, just normalizing along the batch dimension.
Normalize along that batch dimension. That's what it is. Now, a very subtle thing with batch normalization. Why might this be an issue with convolutional neural networks? And this ties to what we talked about with the filters above.
Right. So, I mean, so one, you're just destroying a lot of information, right? That the filters had created. You know, their scale might have been important before.
The scale might have been important. So let's think about with a normal neural network. These are just 9 features.
Sure.
Do I care so much if I scale this feature by a different amount than this feature? Like maybe, but probably not. Like, it depends. Empirically, norming the features will help the network learn, so it doesn't really matter if we scale this feature by a different amount than this feature. However, what's going on with convolutional neural networks? So here's an example of an MNIST digit where 10 different filters have been applied to the same image. Mm-hmm. And so we have a bunch of different output features or neurons where each pixel is a feature. Like that's a feature, that's a feature, that's a feature, and so on.
Sure.
Well, in an image, if we scale these features by different amounts, we might have a problem. Mm-hmm. Because it's going to actually make the image look different. And if we then try to apply filters to this image where one pixel's been darkened and one pixel's been lightened, then we could lose a lot of information.
Sure.
So remember, in convolutional neural networks, when we apply filters to an image, literally each pixel value that results is like a feature.
Yeah.
So what you actually do with convolutional neural networks is this. You actually take each output image. So like this fourth 7 here, take all the fourth 7s that resulted from this batch, and you normalize all the pixels in this image by the same amount. Subtract the mean of all of these pixels and divide by their standard deviation. So that's a subtle thing with convolutional neural networks.
It's pretty cool.
Yeah.
Yeah. I mean, the nice thing about all of this is that, these things are really, they're encapsulated into like layer objects that you would use in code. And so it's very easy to sort of forget these details because, you're hoping that people took care of them correctly for you in the first place.
Exactly. Yeah. You will not have to, I think that's a great point. Like, why are we explaining all this? Why are we going through this? It's not because you're going to have to watch out for this and normalize your convolutional neural networks differently. It's just so that you know what's going on, so you have a richer, deeper understanding of the field in general. If you take Jeremy Howard's Fast AI course, you can write a convolutional neural network in 10 lines of code.
Basically.
Yeah,
it's one of those things where, especially like the very simple, the common tasks have become like almost commoditized. One could say
they have.
But this sort of stuff, even if you see Jeremy Howard's Fast AI class or something like that, it's still pretty clunky, in order to deal with GANs and stuff like that. I mean, it's not 10 lines of code. It's more like, 200 lines of code plus a lot of lines for the data. We're getting there.
Yeah, we're getting there. Certainly, if you're working on some custom problem, your own data set, then it could be very challenging. But if you're working with these, which many of you may in your jobs, but if you're working on side projects like with open source, classic data sets like MNIST,
exactly.
Yeah, not stuff you have to deal with as much. Yeah. All right. So this is where we transitioned in my talk from like all this theoretical, detailed stuff to just looking at some cool results.
Okay, I like that.
All right, great. Raise your hand if you want cool results.
Oh, please.
All right, great. 100% of people raise their hand, so we're going to go on. All right. So this is a cool result. This is from NIPS in 2017, pose-guided person image generation. So this used GANs as part of this framework to synthesize people in arbitrary poses.
Right.
On an image of that person and a novel pose. This didn't get like a ton of publicity, but I thought it was really cool.
Interesting.
In particular, I thought it was really cool because it made use of a really interesting and novel data set. This data set called Deep Fashion. I'll show you this data set. It came from a research group out of Hong Kong.
Okay.
And contains over 800,000 images, which are richly annotated with massive attributes, clothing landmarks, et cetera, different scenarios, including store, street snapshot, and consumer. So what does that actually mean? What's some example data from this data set? They got images of people wearing clothes and annotated different aspects of where the person's body is in the image and where the clothing is. So for example, this is from the paper. Here's a visualization of where all the left elbows are in all the images of people in this data set. So they're all around there. Some are on the right side because the person's turned around maybe. Here's where all the left sleeves are. And so on. And right elbow, right sleeve, you see the same? Yeah. So what's a result from this? So what they did was they took an original, so they basically had images of people in many different kinds of poses. Their goal was to take an image like this and take a desired pose, which is indicated by these dots here.
Right. Right. Hard.
Yeah. And generate the person standing in the desired pose.
Okay.
And then they used another neural network to sharpen the image. Just take this low resolution image, try to generate a higher resolution image.
Yeah.
What they ended up with was this from this. And the ground truth in this case was this over here.
Right. Oh, interesting. Yeah. Okay. Okay.
So it's interesting. It gets a lot of things right that are pretty remarkable. Her hair is on the right side.
Yeah.
Her shadow on the wall is correct. So
Oh, right. I wouldn't have even
what's,
noticed.
yeah, yeah. What's missing here?
It looks like the straps are missing, fine
Straps are
details.
missing. What else? Anything else? No, I mean straps are the big one.
Yeah.
Uh,
Yeah. Yeah. Yeah.
yeah, cool.
The
Yeah,
yeah, interesting. So yeah, how was so Seth, this is kind of an interesting question. We in the previous paper with the sort of DCGain paper, we showed that we could, change things in the latent space in order to get different results. But it was one of those things where the changing things in the latent space gave us, you couldn't necessarily know what the results would be per
yes,
se. The reason why we got the smiling man type of thing was because we looked at the images that were generated from, one latent vector that gives us a woman, one latent vector that gives us a man, one that gives us a smiling woman.
right.
Um, so how do we force the network to put this person in this pose?
Um, that I'd have to reread. You mean how does this actually happen? Where's the GAN come in here?
Yeah, I guess I sort of, the GAN makes sense. It would make sense to me. You can make a GAN that could generate people, but how
Hmm.
do you force them to be in the pose?
That I'd have to reread the paper. I think it's some sort of conditional GAN thing, like they
Yeah.
condition on these points.
Oh,
Um,
interesting.
yeah, that's really the key here. Is they're conditioning on these points.
Okay,
So if these points were in a different place, this woman would be in a different pose.
I see. I see. And
Yeah,
then you might have a neural network that tries to label the points in the um, uh,
the training set, sort
yeah,
of.
yeah, basically that have been generated, and you get some error based on that, maybe
Um, you mean like it generates? Oh, I see. It generates an image, and then you look at the points that were it
predicted.
was supposed to get, and
Yeah.
then you see how. Yeah, and you look at the error. Yeah,
Hmm.
um, could be.
Okay. Okay. Well, anyways, interesting. We'll link the paper here.
Yeah, absolutely. It's in the notebook for sure. We'll make sure we link it and all that stuff. Um,
Let's look at some more results.
yeah, yeah. Well, this is another result I think from this paper. And by the way, the results I'm showing here were not cherry picked. They
Mm,
showed a ton of results in the paper, and I randomly chose these.
mm,
I chose one that was sort of like a model standing with a white background and so on. But another one was interesting. Is a woman sort of in a natural environment. So
mm.
she is standing on the street with a backpack. Um, Here's the new pose, and the GAN generates that. So you can see like still captures sort of red shirt, black pants, like skin tone, all that
Pretty
stuff
cool.
there. Sharpening that up, we get some like background features that look realistic
Right.
based on what the original image was, which is interesting. And there is the actual image right there.
Huh.
So there you go. Um, cool stuff.
Cool. 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 Cool.
So this is some cool results from GANs. Next up, we can talk about semi-supervised learning, which I think we're going to do in a future data talk.
Okay. Let's do it.
Cool.
So once again, thank you all for joining us. I hope you've enjoyed. As always, post your questions and comments down below. So a big thanks from me, Nate, and Seth. Do you want to say some parting words?
Yeah, thank you all for watching. I hope it was interesting.
Okay. See y'all next time.
Bye.